is we're going to send those off to Ahmed Alisa, and he's going to take them to Dr. Faisal Alotaibi at King Faisal Specialist Hospital and Research Center. So he's going to get us answers from Dr. Faisal, and we're also going to get some data from them, because one of the points that both Dr. Faisal and now Dr. Nuha last week brought up as well on the call was that, okay, our models are trained on the information, on the data that we've gotten from ADNI and OISIS, but we also need to factor in the fact that they feel that the Saudi brain composition is a bit different. I don't know, maybe it's because of genetics, or I don't know what it is, but they said that historically that they found that the brain composition for Saudi people or Middle Eastern people is a bit different than the brain composition for people, let's suppose, based in America, North America, or Canada. So we're going to use some of their data as well, which they've happily agreed to share with us, and then we're going to see how where that takes us. So that is the development and from the progress from my end so far. And so far so good. I see Dua has joined in on the call as well. We've got a couple of new people in here as well. Now, for everyone on the call and for the newcomers, please note that the sessions are recorded as well. Muadh has also joined. Yeah, people are slowly going to be coming in. I've got some messages on my WhatsApp. I'm just going to turn this off. So keep in mind that these sessions are recorded as well, and they're uploaded onto our YouTube channel. And then there's a transcript for each session as well. So you can always go through the record stuff that you've missed. You can go through it. And I'm going to hand it over to Helio now, who's going to commence with his presentation. And I'd like to request everyone else to please mute their microphones. Azam, I think you're the only one, so I'm going to mute mine as well.
All right, thanks, Ahmed. Let me share my screen real quick. Let's see, where is the, okay. So, we are presenting, the share screen. Okay, so can everybody see my screen?
Yes, thank you. And for those of you who are new to us, the Elder Laboratory is the James Elder AI Lab at York University in Toronto, Canada.
Yes, that's correct. So hello everyone, good afternoon, good morning for me. So I'm Helio Perroni Filho. I'm Senior Robotics Engineer at the Elder Laboratory. And I'm going to give a presentation today on image classification with deep convolutional neural networks. We're going to cover a couple of topics today, describe the image classification problem, talk about the differences between multi-layer perceptual networks and deep learning neural networks, go over an example of a deep learning neural network, DenseNet, and see how it can be used to perform image classification of MRI images, and then do a quick recap at the end. So the image classification problem is a classical problem in computer vision. It can be easily described as given an image, some image I, you want to assign a label from it from a predetermined set. And for the longest time, the way to do it, the meta architecture for an image classifier, was to do it in two steps. First, you use a feature extractor that would extract predetermined features from the image. And there were for a long time a whole research field of how would you represent an image in terms of different features. And depending on the feature extractor that you use, you would get features depending on texture, color, edges, and so on. But in any case, you would get a vector representing an input image in terms of these features, and then you would use these features along with the levels of annotated image to train a classifier that could be a neural network, a support vector machine, or random forest, what you had, to learn how to associate the labels to the feature vectors that you got from the feature extractor. So I mentioned that one of the classifiers that you could use is multi-layer perceptual neural. or multi-layer perceptron network, an MLP, and this is a neural network composed of perceptron neurons, which perform a biased weighted sum on an input vector followed by the application of a nonlinear activation function. So the idea is that if you have a input vector, each dimension in the vector is going to be multiplied by some weight that's a parameter of the neuron. These products are then going to be summed between them, and with the addition of a bias term that's always the same value regardless of the vector. And this gives you a scalar output, and you then pass this output through a nonlinear function that will give you the final result for the neuron. And mathematically, this neuron would be represented by this formula. The output is the result of applying the nonlinear function to the sum, to the weighted sum of the vector inputs plus a bias. And you can combine these perceptron neurons in networks with multiple levels. The classical architecture is a neural network with one input layer, which would be the vector inputs, one or more hidden layers, at least one hidden layer, and then one output layer that would receive the inputs from the second to last layer and compute the final output. And MLPs can be used for either classification or regression. For classification, each output neuron would represent the unnormalized likelihood that the input I belongs to the class corresponding to that neuron. And for regression, each output neuron represents the value of the corresponding dimension of an output vector. And when you use neural networks in this way, we usually normalize the outputs to the range, or either 0 to 1 or -1 to 1. So, for example, a classical classification task for a multi-layer perceptron network would be classifying the species of an iris flower, and in this case, you would get 4 inputs: the length of the flower sepal, the width, and the length and width of the flower petal. Importantly, the inputs for these networks wouldn't be the image. Someone would have to manually get the image and manually identify these features of the flowers and measure them and write down these values so they could be submitted to the perceptron network as inputs. And then you'd have 3 outputs, each one corresponding to which species of iris flower these inputs might correspond to. And you would decide which species is the output of the classifier by looking at these values and selecting the highest one. An example of regression that you could do with an MLP would be a car controller where you get as inputs the proximity to the left and right curb, the proximity to an obstacle on the front, for example, on the car, and the speed, the linear speed of the car. And then you get 2 outputs: an steering angle in the range -1 to 1, with -1 would be fully for the left and 1 full to the right, 0 straight ahead. And another output, a throttle value in the range -1, 1, where 1 would be full throttle and -1 would be, or any value lower than 0 would mean applying the brakes. So one limitation of MLPs and what requires that we do feature extraction before we use them for image classification is that they don't work well with multidimensional inputs, with special inputs like images. This is called the curse of dimensionality, that as the number of dimensions in an input increases, a method quickly becomes unusable. So in the case of MLPs, if you have a very small 64 by 64 pixel image, that already means that you have 4096 input parameters, which is quite a lot for an MLP. Another even more serious problem is that in image, the feature that you want, that characterizes the object that you want to identify, is in all likelihood not always at the same location and in the same size in the image. So across different images, the same object could have a different position and a different scale in the image, which in the case of a multi-layer perceptron network would mean different and maybe even completely different inputs that the network would have to learn to associate to the same level, and this would require a very large network, even larger than would be required just for addressing all the inputs. A very large network to be able to account for the different cases where you have the same level. So again, the solution is to add a feature extractor, which classically would be something that someone would have to design explicitly by hand. They would have to think about, well, what features do I want to extract from the image and how do I do that? And does anybody guess if their assumptions were correct? You'd have to go out in the field and test this and see if the results are good or not. And really, there is no objective way to determine the best feature extractor because different conditions would favor different feature extractors, which is why you had a bunch of them. And these would be the inputs to a classifier that would learn to associate the input features to the output levels or the output values in case of regression. So the question suggests itself, if we have a classifier that can learn to associate features to output values, could also have a feature extractor that would learn to associate input images to feature vectors that would be convenient for then doing the classification or regression task. And the answer that we got in the 2010s is that, this was in development for a long time, but only until about the 2010s, only by about the 2010s, we got the hardware that made this solution practical. The answer is yes. If we use a convolutional neural network, I'm going to expand on what a convolutional neural network is in a little while. But for now, we can just say that in a deep learning neural network, we combine a convolutional neural network as a feature extractor with a multi-layer perceptron network for classification and regression, or classification or regression. And this allows us to have an end-to-end training of both feature extraction and interpretation. You can have a single network that does the two things, and from training data, from input image and annotations, you can have the whole thing learn its a convenient set of parameters. Okay, so what is a convolutional neural network? These are networks that individual neurons perform convolution between quotes, because what's in the neural network field is called a convolution is actually really a cross-correlation product, a sliding dot product. But let's just go with it. So I know that this formula by itself, it's hard to make out what it means. So let's go with a visual example. If I have a filter that is a matrix that will favor inputs with a specific shape, and they have an image that might have regions that sort of look like this shape. We go over the image with a sliding window, and for each position of that window, we do a a slide dot. We do a dot product between that region of the image under the window and the filter, and the closest the values under the window look to the filter in terms of the relative values, the higher will be the result of this operation. So in a case where we have, for example, a flat input, so all the cells have the same value, the correlation between this input and the filter is going to be very low. So we have a value of 0 here. In a case where the input is somewhat similar to the filter, right? We have here the right side has between the right side and the center has sort of approaching the same relative values that the filter. It's not perfect, but it's somewhat closer. So we get a higher value. If we have a region that looks actually the opposite of the filter, we get a very low value. And if we get and if we have a region that looks perfectly like the filter, we have a perfect match. How would you use this for doing classification? We could have different filters that correspond to specific features in an image. And when these features are present in an image, independently of their scale and of the position, we would get a specific invariant output. So, for example, if I have a neural network of these 3 filters for a diagonal going from from bottom left to top right, another diagonal going from top right to bottom left, and a horizontal. And I had, for example, the letter A. I would get a high output for all these 3 filters because the letter A has both kinds of diagonals and the horizontal. And we would get this response regardless of the position of the letter A, regardless of its specific design, and regardless of its size. So we get a response that is invariant to position and size, and to some degree minor details in the visual elements. Whereas if I get, for example, the letter V, I would get a high response for the diagonal filters and a low one for the horizontal one. And if I had the letter O, I would get low outputs for all 3 filters. So these filters would allow me to classify, for example, different letters as different combinations of filter outputs, regardless of where they appeared in the input field. So a convolutional neural expands on this idea. So just like the perceptual neuron performs a weighted sum of vector inputs, the convolutional neural performs a sum of filtered inputs. If I have any number of inputs, any number of, for example, image channels, these are all going to be passed by the same filter for a specific convolutional neuron, generating the outputs that are then going to be element-wise summed, all added to a single bias, generating a preliminary output. This output is going to be passed through a nonlinear function that's going to generate the final output. And mathematically, we would have this expression where it's the sum of the dot products between the image and the filters, applying a bias, and then this result is passed through a nonlinear function. And I want to notice that schematically, this is very similar to a perceptual neuron. If we go back to the slide of the perceptual neuron, you can see that the formula is very similar. In both cases, we have a nonlinear function. In both cases, we have a bias term. In both cases, we have a sum. The main difference is that in the perceptual neuron, we have a weighted sum of vector values by scalar weights. And in the convolutional neuron, we have a sum of image channels by convolved by a specific filter. And so just like with multi-layer perceptual networks, we can have a convolutional neural network by combining neurons by having several neurons and then having these neurons arranged in several layers, where each layer receives the output of the previous one. One problem that we have with neural networks is the question of saturation of values. Classically, the nonlinear function would be either a sigmoid or hyperbolic tangent that have values capped between 0 and 1 or -1 and 1. And the result of this is that as you stack layers in a multi-layer perceptron with these activation functions, the values start to narrow in range until at the end you have very little to no variation. And at this point, it doesn't help anymore if you add additional layers. So one important development in deep learning neural networks is the use of non-saturating activation functions, where you have a non-linearity, but the output is unbounded in some direction. And the rectified linear unit is the classical example of a non-saturation activation function, where on negative values are capped to 0, mapped to 0, but any positive value is just passed through and modified. Another important element in deep learning neural networks, apart from convolution neurons, is pooling layers. These are used to reduce the dimensionality of an input, which is important because at some point, as we go from layer to layer in the convolutional neural network, we want to narrow down the outputs until we get to single values, which then can be passed to a MLP as a feature vector. And one way to speed up this process is using a pooling layer. For example, a max pooling layer that's going to move a sliding window through an input and always select the maximum value of the under the window. Another important aspect to consider is input normalization. This removes scale differences between across data dimensions and sensitive the data points in the input space. And this can be done in 2 steps. You first having an input, for example, an input image. You first subtract the average of the values of the image, and then you divide by the standard deviation. So you get a normalized value across images. Often you're going to see that instead of doing these operations directly, you go over a data set, you compute the average and the standard deviation for the whole data set, and then you just use these values as constants for the image, which works quite well. When training a deep learning neural network, you want to have your different classes represented more or less equally in your training data. This is not always the case for the raw data sets. Luckily, when we are working with the image, we can use a number of visual operations like translation, rotation, adding noise, that allow us to synthesize additional additional entries for classes that are underrepresented in the raw data set. And this is generally called data augmentation. And finally, when we're training a deep learning neural network, we may want to ensure that different neurons in the same layer are as different from each other as possible. This can be done by using so-called dropout, where during training, we randomly shut down hidden neurons to make sure that the different neurons haven't seen all the data sets. So they are specialized to different subsets of the data set. So between them, they have higher variety. When doing optimization, there are a couple techniques that we can use. This really is going to be a subject for another time because it's a whole lecture in itself. I just wanted to have it noted here that when we do optimization, we have a number of methods to choose from. These are usually more or less stochastic methods, so they combine specific procedure with a random selection. But despite that, at the high enough scale, we get very consistent results from training. So I want to give an example of a neural network, deep learning neural network that does image classification. And this is the example selected is called DenseNet, and this is an example of methods that were developed for improving the performance of deep learning convolutional neural networks. Each layer in a dense block, the network is composed of dense blocks interspersed with transition layers. The idea is that in a dense block, the size of the output remains the same. Between dense blocks, there is a narrowing of the size of the output, which is performed by transition layers. And inside a dense block, we have layers, and each layer is connected to all the layers that come before it. So each layer knows has access to the processing at different detail levels. And just a second, wait. Let me stop sharing for a moment. I want to move to a different window. Let's see. Yes, perfect. Okay. So yes, so I have here a notebook in the Kaggle website. And if you haven't tried it out yet, I highly recommend it. Kaggle is a website where you have access to a wide variety of data sets for training neural networks. And also you have inside the Kaggle website, you have a notebook environment that makes it very easy to access these data sets. And this notebook in particular, I'm going to work with Azam to have it added to the course repository later, but it shows how to use DenseNet to classify MRI image from a pre-cleaned up and augmented Alzheimer MRI data set. And I'm using the PyTorch the PyTorch framework that includes both functionalities for instantiating neural networks and training, and also dealing with data. So it can, as part of the Torch Vision Transforms module, we can specify a set of transformations for input image for training, where we resize them to specific input size, perform a random rotation and flip to perform a data augmentation, and then use normalize. As I mentioned, we use normalization. As I mentioned before, you can go over a data set, find the average and the standard deviation, and then have these values fixed for every input image. Then we can load the data set. We can take a look at examples from this data set. Something very nice that's turned up in the past couple of years is that existing models can be downloaded by most frameworks. In the case of the PyTorch, we have the models subpackage of Torch Vision that allow us to download a pre-trained version of DenseNet, specifically the one-to-one variation of DenseNet. Then we can take a look at its structure, see that, yes, it's defined, it has a number of dense blocks, each one with a dense layer. And then we can customize this model. In this case, we're going to freeze all the layers for the network. So during training, they won't be modified, except the last dense block that we want to be able to modify. And we're going to add a custom classifier at the end. It has four outputs for 4 levels of diagnostic, for non-demented, very mild demented, and moderate demented. And then I'm able to do what we call transfer learning, right? We train this neural network, but only modify the classifier in the last layer, while keeping the rest of the network static. Because as I mentioned, the idea of a deep learning neural network is that you have feature extraction and classification or regression in the same architecture. Well, if you have already trained a neural network on a sufficiently large data set, the feature extraction part is not going to change much. So you don't have to redo that step. You can get an existing version of a neural network, retain the knowledge about feature extraction, and just update the last couple layers to account for the characteristics of our new data. And we train here over 3 epochs, and in the end we get very good accuracy for both the training and the validation data sets. So I got over almost 95% accuracy for the validation data sets. And then we can run the training network on examples from the test data set and check that indeed it's able to correctly classify examples from the test data set. And we can look at the outputs from the network and see that yes, the output from non-demented is a lot higher than the outputs for the other classes. And we can rerun this a couple times. Each time we get a different example. So this case is moderate demented, and the prediction agrees with the ground truth. You can see that the output for this class is orders of magnitude higher than the other ones. And very mild demented, the same thing here again. This would be 0.93, but it's still higher than the other results. All right, let me go back to the presentation. Stop presenting and go to the window. Presentation. Okay, so in conclusion, multi-layer perceptual networks perform feature classification or regression, but they require inputs to be positioned and scaling variants. And we can do this with convolutional neural networks that extract features from multidimensional inputs, for example, images, and these features can be invariant to position and scale. By combining convolutional neural networks and MLPs with other supporting techniques, we can build deep learning neural networks, allow end-to-end training of feature extraction and classification regression. Okay, so this is the end of the presentation. If you have any questions.
I would assume Azam might have some questions for you. He might, Azam.
Yeah. First question, Sir Helio, is that in convolution neural network, I am also training different techniques. You also use transfer learning technique, DenseNet. I also
Hmm.
use a technique, but the problem is that uh, how we balance over class, because in such cases like Alzheimer, the class, some classes have very too much data, like that the mild moderated class have too much data, and we balance the class, we deploy some noise, and we generate some images, which is a technique to balance the class. But are you suggest that this technique, but I feel that sometimes the model is too much overfitted reaction in such type of solution, and which type of transfer learning is best form the training of, because I use ResNet also, AlexNet also. These all are transfer learning models available the weights in the site of Google and something else. How you suggest that to balance over class and fine tune over model for the best prediction?
So yes, this is a challenge and as always an open problem. The classical approach is to use data augmentation. So you get a higher number of examples from the represented classes. Uh, there is a technique, I forget the exact name. It's not I think it's regularization, where you add a term to the to your loss function that favors smaller values in the network parameters, so that you get a smoother decision surface, and in that case uh, too you're not fitting specific examples too closely. But this is an active field of research, and I'm I'm not sure if I sent you some examples of recent network architectures that do MRI classification, uh, but I'll look that up and get back to you.
My second question is that in our case, we are dealing the MRI, and you know that the MRI have a 3D posture of the images, and in similar case, you train the network. I also train some examples, some data set choose from Kaggle, and which are already available in data augmented form, pre-processed form. But I also built some model from scratch, from selecting the data from adding in the 3D format, and convert 3D format images after pre-processing to 2D and built a network. But my question is that when we deal from the raw MRI data, uh, we deal all the three angles of our MRI, and are you suggest that we prepare a data from all the three angles, and then after combine the results and then classify that which type of Alzheimer class is exist? Yeah, are you suggest that we train our model on 3D? But after the experiment, I feel that when we train the model directly on 3D convolutional network, results are not too much good. The accuracy is not up to the mark. But when we expect all the 2Ds of all three types category, just like MRI, axial view, corneal view, and sagittal view, we get a better results. And lastly, one thing is that I also um, feel that when we made a hybrid model, just like that, to train the model on DenseNet, if we train our model in a way that DenseNet and some other uh, uh, transform learning technique and make a assembler and get the data of such assembler, I think it's better way to um, overvaluate our model. Are you suggest that this technique is better?
Yes, as you just said, there are different ways to process MRI data. We can use 3D convolutions to process the 3D data directly. We can combine an ensemble of 2D convolutions at different axes to generate a final result. I suppose that the fact that you're getting better results with the second approach is because there is really an advantage to using ensemble learners. This is actually a technique called boosting. That idea is that if you have a classifier that is just better than random choice, if you combine a sufficient number of outputs of different versions of this classifier with a voting system, you can actually get much better results. So the difference in performance that you're seeing is probably due to this. And if we went ahead and instead of having one classifier per each axis, we had two, three classifiers, maybe using Bayesian learning to have a random distribution of parameters, a normal distribution of parameters for these networks. But maybe we could see even better results. But again, this is something where we should really take a look at what's the current state of the literature, and since there is a lot of research on this area.
Yeah. Okay. Fine. Somebody want to ask the question to Sir Helio? Overhead to Sir Ahmed.
I think those were a couple of good questions from Azam. Azam, if you have any other technical inquiries from Helio, you can always email him as well. And aside of that, what I would like to do before we go is, so I've started this thing that every week one of our internees is going to introduce themselves. I know Zian had the introduction yesterday. But Ahmed Alisa, I see that you're on the call today, as always. That's very good. You're very punctual. Why don't you tell the team a little bit, maybe a couple of minutes, tell everyone about your background, your education, and currently where you're working with King Faisal, and tell them a little bit about that side project that you have going on. I know you wanted to discuss it with Helio as well. So just a couple of minutes, if you can just give us an intro. Thanks.
Thank you, Mr. Farooq. Assalamu alaikum, everyone. I'm Ahmed Alisa, a fifth-year medical student. I have been, my first 3 years were at the university, but my fourth year and fifth year are in the hospital. Right now, we're finally gaining some clinical experience. I have started learning about AI when ChatGPT became popular last year. If you don't remember ChatGPT 3.5, that's when I got into AI. I was really fascinated by
Ahmed, sorry to cut you. Please, if you could tell them which university and which hospital you're at.
Right. So I am a medical student at Al Faisal University in Riyadh, and the hospital I'm currently in is KFSH, King Faisal Specialist Hospital. And as I was saying, I got into AI. I really liked especially videos about how LMMs works, large language models, and how was it trained, and neural networks, and all of this stuff. I have been trying to study on and off. I did some light projects, like I made like a local off-the-shelf model, run it on my laptop, some small stuff, nothing big. Yesterday, I discussed my idea with Ahmad Farooq, and I want your opinion, Mr. Helio, about it. Basically, by any chance, do you know what aphasia means?
Sorry, come again?
Aphasia.
Oh, aphasia.
Aphasia.
The term isn't strange to me.
Is it a
something
diagnosis?
Yes, basically, it's one of the complications that can happen after a stroke. The person will not be able to speak. He will either be mumbling or some weird sound, but he will not be able to speak as he was previously doing before.
Right.
So I had this idea about training a model where first, after training, making the base model, we will personalize for each patient. He will mumble. You will have like common phrases, and the patient will try to mumble these words. And this is basically the setup process, so the patient can learn what these decipher what this mumbling means. After that, there will be a speaker attached, and whenever he's in a real life scenario, he can just mumble whatever he wants, and the AI will be able to understand what he means and speak it out loud. And another thing we can add is also to input his old, if he had any voice recording with old voice, we can input it in the model so it can speak on his behalf. Like the entire idea is just like having a prosthetic limb, but for voice instead of arms.
Yeah, that's a really interesting project. It's a question whether there is enough variety in the person's mumbling to be able to reliably differentiate between different intents, right? Do we have any research data suggesting that when a person wants to say, for example, good morning versus I'm going out, that the mumblings are consistently different in ways that could be differentiated?
Yes, there's actually some Arabic papers about this exact topic, and especially use the model Whisper. Yeah, I'm not sure if you know.
Yes.
Yeah, they were able to train an aphasia model. They used two models from a TikTok datasets and another from an aphasia data bank. They mentioned in the paper that having only one of them leads the model to forget how to speak the other. But for example, if it was only trained on aphasia patients, it will not be able to actually speak in a language that normal people can understand, and vice versa. And they ran on an edge computer with 39 million parameters, and their results were quite good. I can send the paper later if you want.
Yeah, all right. So yes, this looks a very interesting subject, and here at York, in the next couple months, we are going to start a new research project about developing technologies for independent elder living, and this might be an interesting topic to develop in that project. So let's get in touch.
Sure, sounds great.
See that there is a message from Maham Siqu. I actually joined this meeting through an ad and got really curious about the research. I'm going to be working on a research assistant in machine learning in Istanbul, and I'm spending some money yet. So I wonder if there's any way I could get involved with our intern with your team. Love to know more if it's good fit.
Yes, of course, Maham. Please do email me. I've just sent you my email over there. And also add us on LinkedIn. And it's wonderful that you came on the call today. And sure, we'll fit you in with the team, and we'll give you some tasks. And we'll send you a link to the training session for every week as well. So yeah, I think it's a good opportunity for you. So do email me, please. Perfect. And does anyone else have any more questions, or should we let everyone go?
Mm-hmm.
I guess I have a question. Um, is the DenseNet model the optimal model, or yeah, like have you tried others and this one has shown the optimal results?
Yeah, no, the DenseNet model is a relatively old model. It's from the original paper is from 2016, so nearly 10 years ago. I just selected it because I wanted to have something that would be easy to set up as an example for the students of the course. But yeah, having a state-of-the-art model up and running would be a whole project in itself. It's left for the students as an exercise.
All right. And I guess a follow-up question to that would be, is the deeper the model is, does it necessarily mean accuracy, or is that not true?
Yeah, just like the classical multi-layer perceptron models had limitations in terms of how many layers you stack at some point doesn't add any more value. It's still the same thing is still true for deep learning models, even though deep learning techniques have increased a lot the limits of how many layers you can stack in a network and still get something useful out of it. And again, it's a frontier of research, finding new ways to increase the size of the network and still get something useful out of the increased size. The idea that you can just scale up the network and it's always going to be better is naive. And there are some people in the chatbot industry that are about learning this now the hard way.
I see. I see. So is there like a specific optimal number or for each task, or how does that work?
Yeah, not exactly, because the search space of neural network architectures is so vast. It's hard to give it's very difficult to give a hard limit to say, well, more than 176 layers is useless. It depends on the particular architecture that you're using, the particulars of the problem, and at some point, it gets really hard to do experiments at scale, right? If you have a really large network that takes 3 months to train, you're not going to be able to try many variations of the architecture, because it's a big commitment to train any one variation, right?
I see. Thanks a lot.
My pleasure.
So Helio, one question is from my side. In some
Yes.
time, you use some transfer learning layers like DenseNet, ResNet, and you do not set the early stopping on over transfer learning. And I am trying some experiments that your model going to overfitting if you are not selecting proper learning rate, proper early stopping over model. You suggest that is a better technique? Um, yeah, you suggest some optimal hyper tuning values from the better performance of CNN models um, in case of transfer learning?
Sorry, as I'm not sure I understood the question.
I am saying that when we train the model, uh,
Hmm.
uh, by using the transfer learning like DenseNet and other, and we are not selecting the early stopping value in the training of a model. Early stopping means if a model goes optimal value at the epoch, certain epoch, our model training stop that. Sometimes you do not set the early stopping in your training. Your model moves to loop, which you select that, you select 50 and 100, you move your evolving that and training that, and in such case your model are too much overfit.
Yeah.
And are you suggest that the early stopping is necessary from training?
Again, it depends. We if different problems, you're going to have different results, right? And yes, in some cases, you need to do early stopping, otherwise you get an overfit network. In other cases, the more you train, the better you get, and it really depends on the size of your architecture and how well it fits the problem at hand. If you have a neural network that has enough capacity, enough variety capacity, uh, maybe for the particular data set that you have, you're not going to reach a point of overfitting. And the more you train, the better you get, although there is an asymptotic limit that you're not going to get better than some threshold value, but you're not going to get worse. In other
Uh,
cases, yes, if you go past a certain number of epochs, you're going to start overfitting.
uh,
It's
uh,
that's what the challenge with deep learning software development, right? Because there is no predetermined, there is no mechanical set of procedures that you have that you could follow. You have to look into what other people did with similar problems. You have to see what the state of the art is in terms of architectures, what other people have tried in terms of combinations of training techniques, and you have to do some experiments and see what works.
my last question is that how you suggest that, because I am doing most of experiments on both technologies, TensorFlow and PyTorch also, and I observed that in a practical way, when we deploy the model in the production side, the PyTorch is best. But in case you are uh, many experiments doing in the fast run, I think the TensorFlow is bad. What's your suggestion?
Yeah, then I'm sorry. This must be really frustrating, but yet again, the answer is it depends. Because in terms of a popularity, it's clear that today PyTorch is by far the more popular architecture. So if you're working with PyTorch and if you want to try different architectures, chances are that you're going to be able to find something that's close to what you want to do written in PyTorch. But Google still keeps their framework TensorFlow in the run by uh, making available the tensor processing unit, the TPUs, which are very efficient, and they have some very good models available through the framework, and that would lead you to prefer TensorFlow in some specific cases. In our case of MRI classification, I would suspect, since this is a field with very active development, that in the end our hand would be forced with using PyTorch, so we have better access to existing models. But yeah, we have to look into what Google is doing in this field.
Yeah, I also feel. Okay, thank you very much for your valuable suggestions regarding the technology and other things. If
My pleasure.
somebody have a question to ask on.
Thank you, everyone. Thanks, Azam, and thank you very much, Helio, for taking the session today and for all the answers that you provided. It's good to know that we have a good, strong, solid AI background people with us, and all the students can obviously take benefit from that. As always, I always encourage people who are working on their side projects as well, like Ahmed Alisa mentioned today. They're always welcome to reach out to us, to Helio and to Hazem, for help and assistance, and they're always very happy to do that. Inshallah, we will pick this up next week. Next week, Azam will be taking the session back to his usual routine, and we will see you all there. And have a good weekend, everyone.
Bye bye. Have a good weekend, everyone.
Bye bye. Thank you, Helio.
Okay,
Thank you.
Allah
Bye bye.
Hafiz for all. Bye bye.